we're continuing with our circles, so let's put a circle in here. They don't have a starting. They don't have a starting or an end. Well, a start, but they don't actually have a start. Did you ever go to a wedding? The preacher will talk about this ring. I did a wedding one time. I did a wedding one time where the preacher doesn't always talk about the ring. Shh, I'm talking. They don't usually talk about the ring, but sometimes they do. They'll say it has no beginning, has no end. You probably heard that kind of stuff before, haven't you? And it's talking about their life and and all that kind of stuff. But I had one preacher guy did this. He said he held up the guy's ring and he held up the girl's ring and he put the girl's ring right through the guy's ring because his finger was much bigger than the girl's and it went right through it and he said something like that means like the man is in charge of the woman and stuff like that. And he was a very conservative kind of guy and it was pretty funny because that wouldn't float in a lot of places, but in his church they kind of expected him to say that. But anyway, just thought I'd share that with you. Let's do this. Let's have a chord right there. All right, so there's a chord. Call it AB. Now watch what I'm going to do. I'm going to copy and paste that chord. I'm going to put it over here. I'm just going to rotate it just to show you it doesn't have to be in the same direction. But watch. I took this chord. Now it has the same length as AB, doesn't it? All right. So right there. Oops. And we'll call this CD. Now remember, the lengths of these chords are the same. All right. So I'm sorry. Yeah, the chord. I was right. So line segment AB equals line segment CD. Actually, I don't need to put the segment over top, but we'll say the length of AB is equal to the length of CD. So we have a theorem that says this. In the same circle, okay, or in congruent circles. This would work if you had two circles that were congruent to each other, that were exactly the same. It says two minor arcs are congruent if and only if their corresponding chords are congruent. So what does that mean? That means if these two chords are congruent to each other, so if AB is equal to CD, look at the arc that AB cuts off. It cuts off arc AB, doesn't it? You see that? And it's a minor arc, so we can just call it AB. So this arc AB is going to equal this arc CD if it's cut off by the same exact chord. I shouldn't say the same exact chord, but the chord of the equal length. Does that make sense? Okay, so if you know this is true, or for instance, let's put some numbers in here. Let's say AB was 5 inches, whatever, and then CD was 5 inches. What can you say about the two arcs, AB and the arc CD? They would be congruent as well. That's what that theorem is telling you. All right? And it kind of makes sense that that would be true, doesn't it? Well, congruent, equal. Remember, it doesn't really make that much difference. I don't care. I don't yell at you because I've told you from the beginning, I don't really care if you make it congruent or equal. Some teachers do. I don't really care. You can just put equals. Now, if triangles would be a different story. If it was a triangle, I would say congruent. But not with line segments or angles and stuff like that. Okay, anyway, so that's what that says. So if this is 5 and this is 5, and let's say this is 70 degrees, then what would arc CD be equal to? 70 degrees, exactly. And you know what they could do with this? They could make this like x plus 3 or something like that. And, you got to set them equal and all that good stuff. All right, that was pretty easy. Does that make sense? Pretty simple. What if you had the other way around? What if you didn't know that these two line segments, these two chords, were equal to each other, but you did know that arc AB is equal to arc CD? What do you think you can say about the two chords? Yeah, the two chords would be equal as well, all right, because it's an if and only if. If you look at the statement on Theorem 10.2, it says, in the same circle or in congruent circles, two minor arcs are congruent. Look at the next statement. If and only if. That means it goes both ways. So let me just show you something. You might see this sometimes. So if the chords are equal, I'm sorry, let's say it like this. Let's not say it like that. Trying to think of how I can say this. Okay, so in the same circle, if you have two minor arcs, if two arcs are congruent, okay, so if your two arcs are equal to each other, if and only if. Sometimes you'll do this. They'll put IFF for if and only if. You ever see that before? Probably not. So the arcs are equal if and only if the what? The chords are equal. Now, this if and only if means it goes both ways. So it means if this is, right, the arcs are equal if the chords are equal, then what could you also say? The chords are equal if the arcs are equal. You see that? So it goes both ways. Because a lot of times we would say if the arcs are equal, then the chords are equal. Then you could switch it around and say if the chords are equal, then the arcs are equal. So instead of saying those two statements like that, you can put it together in one statement, put if and only if. Now I just shortened it, IFF, but in the book they say if and only if. It just means it goes both ways. So really it's the converse, right? The statement is true and the converse is true. If that's true, then you can say if and only if, right? Sometimes they'll do this. Sometimes they'll put like an arrow, like a double arrow kind of looking thing, right? Two lines and an arrow going both ways. Sometimes you'll see that instead of IFF. But I've seen that before. I don't know if I'll use it anymore, but there you go. All right, enough of that. I think we beat that to death. Let's see what else we have. There's an example on page 702. I'm not going to take the time in class to do that. I think you can handle that one. But if you want to look on page 702, I'll write that down. Page 702, you can look at the example. All right, and you can follow that. That shouldn't be too hard. All right, let's do another. Oops. Use colors this time. Sorry. Yeah, you got to remind me. I'm usually pretty good about remembering the colors, but tell you what, let's go back and grab my circle right here. There we go. You want a pink circle? There we go. Is it pink enough? It's about the only pink I have. Let's see. It says, make it what? Make it thicker. Is that better? You're welcome. It says, if a diameter or radius of a circle is perpendicular to a chord, then it bisects the chord in its arc. Okay. This is important. You're going to use this quite a bit for some problems. I mean, I can picture the problems already on the quiz and on the test where you're going to have to do this. So let's say you had a diameter right there. Now this works with the radius as well. Okay, you could just start from here and go to here, but I just put the whole diameter on there. And it says, if it's perpendicular to a chord, so I need to make, let's do this in a different color. Let's have a chord, and let's have this diameter perpendicular to the chord. So is my chord going to go like this? No, it's going to go, right, it's going to perpendicular like that. Would you agree? Okay, so if the diameter is perpendicular to the chord, and let's put a little right angle symbol there, what does it do? Well, what does it just look like it does? And probably what you think it does is actually what it really does. What do you think that diameter, or the radius, right, if you just want to consider the radius, what does it do to that yellow line right there? Splits it in half. That's right. So what's a good geometry word? It bisects it. So this segment and this segment would be equal to each other. And if you wanted to put some letters in here, you feel free to do that. Okay, so I could say that AC equals BC. But it also does something else. Look, it goes, what arc does this make? This makes arc AB, or AD, sorry, and it also makes arc B, oops, that's a little squiggly. It makes those two arcs right there, doesn't it? So what do you think that diameter, where do you think it hits? See that big arc AB? Where do you think it hits on AB? It's the middle of the arc, right? So it also does what to the arc? It bisects the arc. Very good. So a couple things you could say. So in this situation, in this scenario, you could say that AC equals BC, right? And you could also say that what? Arc A what? D equals arc BD. Say DB, doesn't matter if you say that. My arc's a little weird looking, but anyway, you get the idea. That's a pretty important thing. Okay, you're going to see that quite a bit. We're going to be doing some things that might be a little bit more complicated. We're going to be given some sides, and we may actually want to do an example. Yep. Yeah, we only have one more thing to do. Let's do an example with this right now. Is that all right? So let's just copy this circle, go down here again, and let's just draw it like this. That goes like that. This goes like this. Alright. You could extend this, make it a diameter. It doesn't make any difference. Diameter, radius, it doesn't make any difference. Alright, so here's our situation. It is perpendicular. They tell you it's perpendicular. Right there. And let's put some stuff in here. They say that the diameter of GH, so GH, so they say that GH is 30. Alright? And they tell you that chord KM, this is KM, alright, they tell you that KM is 22. And they want you to find JL. J is the center, and L is this point right here. I'll put a L right there. Okay? So, where do we start? Well, let's put some stuff in here. GH is 30, right? KM, this whole thing is 22, and we're trying to find JL. We're trying to find from here to here. Let me, we'll just do it in a different color. That's what we're trying to find, that length right there. So how in the world are we going to find that length when I know this whole thing, GH, and I know this whole thing, KM? Well, you have a right angle, don't you? So maybe we want to do stuff with right triangles. But do you see any triangles in here? Okay. Yeah, you could go to JK or JM, right? Maybe that'll help. We'll just do a straight. We don't have to do it dotted, but we'll just do it like that. Different color, though. Now I got a right triangle. Is that helpful at all? Okay. Good. Is it? Yeah. Because the diameter is 30. Good. So the radius is... And JK would be 15, wouldn't it? Okay, because any radius on here, doesn't matter where it is, it's going to be 15. Good. You got it. So KM, that whole thing is 22. Now remember what we just said about this. If a diameter is perpendicular to a chord, it means it bisects the chord, doesn't it? Okay, so that must mean it bisects. So if that whole thing is 22, then this thing right here has got to be 11. And now we can just use what? Pythagorean Theorem to find that. Because GH is the diameter, so the whole diameter is 30. So that means GJ would be 15, right? JH would be 15, and JK would be 15 as well. And sometimes people don't realize that, because remember, this is a radius. So let me do this. Boom. Okay, watch. See, it's the same distance around the whole thing, isn't it? See, it's the same as that, and it's the same as that. Would you agree? All right. Okay. And now, yeah, you just do Pythagorean Theorem. Just put an x right there, and you do Pythagorean Theorem to solve for x. You can do that on your own. You don't need me for that, do you? Okay. So does that help a little bit? All right. So that's all they ask for in this particular problem. Actually, they ask for oh no, that's all. That's it. Yep, that's all they ask for. That was easy, huh? Well, we got one more thing, I think. Let me make sure. Yep, it looks like there's just one more thing. Yep. Right there. Okay, this says... Alright. You good with that? Let me copy this. Let's make this a different color. Let's just make it yellow. Is that alright? Alright, here's another theorem. Let's go green this time. And it says... In the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So let's just do a chord right here. It says it's equidistant from the center, the same distance to the center. Well, how do we show the distance? It's perpendicular, that's right. If I say the distance from this point, what's the distance between that line segment, that green one in the center? It's the perpendicular distance, isn't it? So I would have to go like this. All right. So what does the thing say? It says in the same circle, or incongruent circle. Okay, we're in the same circle. It says two chords are congruent if and only if they are equidistant from the center. So if I had another chord, just copy and paste this, and I'll just rotate it just a little bit just to make it look a little different. Watch this. What if I had another chord in here and it was the same exact distance from the center? So we got to make it perpendicular though, don't we? All right. So here's two chords, and I told you that that distance of that chord, the length of that chord, and the length of that chord were exactly the same. If it's perpendicular to this, guess what might be true about those two green ones? Those chords are going to be exactly the same. Does that make sense? And if they're exactly the same, look what it does. This is a radius. Well, it would be a radius if it kept on going, right? Okay, because it does go through the center. So if it kept on going through the center, where does it hit that chord? If it's perpendicular, we just learned it, it's got to hit it at the midpoint, right? So it bisects that chord. So there's a lot of stuff you know about this. So if you know these two things are equal and it's the same distance away from both of those chords, those two are going to be equal, and that means those two chords themselves are going to be equal to each other. You get it? So if this bisects it right here, this bisects it right here, guess what? All four of those little pieces, watch, that little A, that little B, that little C, that little D, they would all four be exactly the same, wouldn't they? You okay with that? Okay. And let's see. Yeah, we should probably do this example, don't you think? We got some time. We got some time, so... Alright, let me try to draw this thing out. This looks like it goes right there. And then this looks like it goes there. And that looks like it goes there. And let's do a different color here. This, oops, see daisy. Forgot to, got to click off of it if you want to make something else a different color. Forgot. And let's say that this is perpendicular and this is perpendicular. Does that look pretty close? Pretty close to perpendicular. And, well, if it's perpendicular, let's make sure we put the right angle symbol in there. And what do they tell you? They tell you that this little bit right here, this green one, is 5x. Oh, this is really easy. And this is 3x plus 4. Yeah, and it tells you that, let's put the letters in here. W, X, Y, and this is B and C. Alright, they tell you that WX is equal to 22, and so is YX. YX is also 22. So that means these two chords are equal to each other. The distance between them would be what then? If the two chords are equal, what's the distance between them? They got to be equal as well, right? So really, the math was pretty easy here. It's just understanding why that they're equal to each other. Do you get that? All right, so it's basically just the theorem that we use. It's kind of like the converse of what we used. Whereas they told you that the two segments were equal, the two chords, I should say, were equal to each other right here. And then find this and find this. And I think that's all they ask you to find. Oh, no, they ask you to find AB, which is pretty simple. Okay, you set them equal, you solve for x, you plug it back in. X is 2. If you solve for it, plug it back in, and that's 10. So if that's 10, that's 10. We okay with that? All right. Yeah, that wasn't that hard at all. Wow, when's it going to start getting difficult? I don't know. Maybe never. I'm liking this chapter so far, aren't you? Yeah, I like the circle chapter. I think it's kind of nice. All right, let's do some problems. Pages 705, 706. And 7 to 23. Now it looks like I'm giving you a few extra problems, but I mean they're all kind of easy though, so it shouldn't take you much longer than it takes on a regular lesson. So we'll do 7 to 23 and 31 to 33. Okay. Yeah, last night I gave you a few extra, but I mean it wasn't hard. I mean a lot of those you can almost just look at, right? And just yeah. Yeah, so even though it was some extra problems, they weren't difficult problems. All right, there you go. Right. The over 360 and all that stuff, yeah. Yeah, it's just calculator, exactly right. Okay, and this probably is not much different. Maybe a few little algebra things, right? You have to set a couple things equal to each other, solve for x. Not that big of a deal. Yep, all right, that's it.